So last time we covered this first example of a DFA. I guess before we dive too far in, I should note that the assignment is posted. You should take a look at it. Let me know if you have any questions about any format expectations, about how you're planning to submit the assignment, how you're planning to work on the assignment. We can get those clarified as quickly as possible. Yeah, let me know if you have any questions.
I assume you take latex, the documents, does that work?
Yeah, that works. All right, so if there were no questions about this first example problem, we can dive straight into the second one. Were there any questions, any notational questions about how this finite state machine accepts the language prefix AB over the alphabet AB? All right, next one. Find a DFA. Now we're doing binary instead of AB. You want to accept all strings except those containing a substring 001. So as soon as we see a 001, we say nah. Anyone having any questions getting started? Come up with during the process? Anyone have an answer?
Well,
Couple people, close. Probably good enough to go over. So I've notationally been labeling states starting at Q0, Q1, Q2. I'm going to take a slightly different approach this time and try to find the logical meaning of each of these states to show that you don't have to label the states in a particular mathematical fashion like this. You can choose to do so if it makes sense to you, but just like your own variables, you can label states however you would like to. As long as it's clear. So we're going to start with just an initial state. So we know that we need some arrow pointing at that state that says that this is a start state. I'm going to label this state with lambda, just showing that we have seen no part of this substring so far. And we will see that the labels of the states will map to the amount of this substring that we have currently seen as we've been parsing our input. So we need outputs from this for a 0 and for a 1. Which one of those is easier to handle for you? On a 1, what should we do?
in the same state.
Loop to the same state? I like that. This says that we still haven't seen any part of the substring 001. We don't immediately want to reject or move into a trap state like we did last time, because the substring 001 may still come later in the string. What do we want to do on a 0 from this state that we're labeling lambda?
State.
New state. I like that as well. Let's, on a 0, transition to some new state. I'm going to call this state 0. Because it represents the amount of the substring that we have seen so far. We've seen a 0. Great. Now, we still don't have a total function. We need to define what happens on a 0 and a 1 when we leave this state. So, assuming that we've seen a 0 so far, what happens if the next character in the string is a 1? Where should we go? What should we do?
Back to the beginning.
Back to the beginning? We're going to move back here. It says, we saw a 0, but it was followed by a 1. There's nothing that we can follow that with that will do more work toward this substring. We now need to see the entirety of the substring from the beginning again. Does that make sense? What should we do on a 0 from state 0? Another new state? On a 0, we are going to go to some new state that I'm going to call 0. This is the amount of this substring that we have seen so far. Now we need to define transitions out of this state. What happens on a 0? Makes sense, right? Because if you see 0, then that's, you still have seen the first 2 elements of the substring. So we don't want to go all the way back to the beginning. We don't want to go back to here. We've still seen 2 zeros in a row. We've actually seen 3, but for this substring, we only care about the last 2 that we've seen. So yes, on a 0, we're going to stay here. On a 1, what should we do? Some kind of trap state? We're going to call this the 001 state. What should we do on a 0 and a 1 from this? It was spoiled here by the concept of a trap state, but we want to stay here because we've seen that substring. No matter what we do from here, we don't want to accept it all. So we are going to loop here on a 0 or a 1. There's one part of this we have not considered or done yet. Which of these states are final states?
The first 3.
All of the first 3?
Yes.
Remember that by the definition of a DFA, we don't need only one final state. You can have any number of final states. So yes, if we finish parsing the input string and we are at any one of these first three states, we accept. If we somehow manage to make our way to this trap state, then we reject. Does someone want to give me some binary string so that we can run through an example of exactly what these transitions would look like, where we would end up?
0, 1, 1, 0, 1.
0, 1, 1, 0, 1. So according to this finite state machine, we start here. We transition from here on a 0, then a 1, then a 1, then a 0, then a 1. And since we end up in this state, it is a final state, so we accept this string. We can make a logical jump at this point and ask ourselves, all right, does this string contain the substring 0, 0, 1? And that can help you to determine, is this a correct system? It's kind of like a unit test. It doesn't mean that the system that you created is correct. It just means that it's correct on this particular input. But as humans, we're very good at finding patterns and meaning in things. So as you go through some of these unit tests, these examples, as you run through your system, you might go, wait, but if this were, instead of a 1, this were a 0, I wouldn't be doing the right thing. So going through and just practicing this is good for making sure that the systems that you design are sound. Questions on this state machine or why it solves this problem? Any of the notation? Any of the logic used in constructing it? Level of confidence on this, just giving me a set of thumbs. All right, we will move on. Remember that I do record these lectures and they are posted on my YouTube site that is linked in Canvas. So if you want to go through any of these, watch them be derived again, go through this process again as you're studying for either homework, trying to get something down, or studying for an exam, all of these do exist. So here's another representation just because I'll upload the slides and I want you to have access to a solution without having to refer back to and finding this point in the lecture. I'm going to introduce a new concept before we get a couple more practice problems. And this concept is a regular language. So there are multiple different types of finite automata. The DFA that we have covered so far does accept this kind of language. They're linked. Regular languages and DFAs are linked. So you can now imagine what are the limitations of a DFA. If you could somehow quantify what kind of language could a DFA accept, does there exist a language that a DFA could not accept? We call the set of all languages that a DFA can accept a regular language. And we will see that there are other ways to define this concept in terms of other constructs as well. But there is a limit. There are languages that cannot have a DFA constructed for them. We'll kind of come back to that and try to see if we can formalize that and come up with some intuition for it later. So we'll just call a family a set of languages. So regular languages are the family of languages that a DFA can accept. Okay, we'll actually go into it now. I've already spoiled this, but the family of languages accepted by any DFA is limited. We'll go there. Why not? What is that limitation? What's missing from the concept of a DFA that maybe you've seen of or heard of or is useful to you as you're writing your own programs?
Your plan for the fact that it has to be a pure function. So the transition function has to be pure.
Is total? That's a good idea. We will find that we actually have a structure that does not require total functions that also is restricted to regular languages. That's a really good guess. That limiting factor is a finite amount of memory, which is quite interesting. Like we saw the substring 001. So if we needed, for some reason, to be able to find the family of languages that are palindromes, however many states we create, that's how long the palindrome can be. As soon as you find a string that is a palindrome that has more than that many ins and outs, then we would need a bigger DFA for that. And in fact, we would need an infinitely large DFA to be able to find the family of languages that is all palindromes of an arbitrary length. So as soon as you find yourself needing more and more memory, we end up needing to move on from DFAs and define some other structure that can handle an infinite amount of memory storage. So with that intuition, we're just going to, the important thing from here is just defining that any language a DFA can accept, we're going to call regular. Now we're going to get into an important type of problem that we can solve. If we want to prove that a language is regular, how could we do it? So I give you a language and I say, is this language regular? The easy way is to say, yes, it is regular. The really difficult thing to answer is, no, it is not regular. And we will go over that as well. But how would we say, yes, it is regular?
Make a DFA?
Yes. Construct a DFA that accepts that language. Since we know that any language a DFA can accept is regular, then we can prove that a language is regular by constructing a DFA for it. So this is an important thing that we need to be able to do. So now, the same kind of problem that we've been doing, construct a DFA that accepts this language. Now we can reword as prove this language is regular. And the way that you will do so is to draw a DFA for it. So now we can say, and we're going to introduce a little bit more math terminology here, show that the language L, we have AWA, such that the W in here is in the star closure of the language. That basically means any set of A's and B's. So if we wanted to state this entire thing as English, how would you succinctly describe this in English?
Arbitrary number of characters with A and B in between two A's.
Yeah, basically it's a string that starts and ends with an A. This is just a mathematical concept that says whatever's in between that doesn't matter, it's arbitrary. It could be empty because it's the star closure, not the positive closure. This just says 0 or more characters that are either A's or B's. So now, to show this is regular, we just need to be able to draw a DFA for it. So let's go do it. If you'd like to work in pairs, feel free to make a friend. If you'd rather be an introvert, that's okay too. Think they have a solution? Some of us. Maybe if you three want to compare notes on your solutions, see if you can verify that you have something that is logically equivalent. It may not be exactly the same DFA, but we did mention before that there are multiple DFAs for the same problem. Yeah, go ahead and see if you think that all of your diagrams are the same, or if there are differences, why are there differences?
Yeah, so they can go back and forth, at least one. Yeah. And then second day, so it's final state. So they'll end up just on something. Yeah. Looks like. Yeah.
All right, I'm gonna go back to my Q state terminology for now. And so we get some experience seeing these as different things, you can label them as interestingly as you'd like to. So what happens if the string that we see starts with a B? We need some kind of trap state because no way can we start a string with a B that adheres to this restriction. A string that starts and ends with an A. So on a B, we are going to transition to something that I'm going to call Q trap. I could label this as Q1 or Q2 or anything, but just like in coding, if you have variables that you name them, that makes it a little bit easier to see what your program is doing. If you label some states as something that's a little bit easier, and yeah, I just find that it's nice. So we'll loop to itself on an A and a B, definition of a trap state, there's no way out. It gets a little bit harder from here, so we need to figure out what happens on an A. We obviously don't want to go to the trap state, so we're going to go to a new state. On A, we're going to go to a state that I'm going to call Q1. From here, should we be accepting? Have we adhered to those restrictions? No. So it starts and ends with an A. We need to at least see the starting A and the ending A. They can't be the same A. So that tells us that on an A at least, we want to move to some other state that we're going to call an accepting state. Because we've now adhered to the basic restrictions of this. What do we want to do from Q1 on a B?
Or make Q3 and move to it.
Make some kind of Q3 and move to that Q3. I would argue that we have all the states that we need.
You could just stay at Q1.
You could stay at Q1. Why does this make sense? Why is this something that we could do here?
Because if you're out of B, then it means you're ending on a B, which is bad, and Q1 is in the final state.
Right. So we still haven't seen that last A, but Q1 says we've seen the first A. And we have not yet seen the last A or something of the sort. But we still, it would be easy to stop here and think that, all right, we solved the whole problem. Have we solved the whole problem? No. This DFA doesn't have any way to talk about something like an AAA or strings like that. So from Q2, we need to figure out what we're gonna do. On an A, what do we do from Q2? Stay there. So now this becomes the last A, the A that terminates the string, if we stay there. But if we see a B, suddenly the A that transitioned us to Q2 wasn't the last A. So what should we do when we see that B?
Return to Q1.
Return to Q1? I like it. We still know that we saw that first A. The string started with an A, otherwise we wouldn't have gotten to Q1. We can't teleport from the trap to Q2. So we know that the string still started with an A, but now it hasn't ended with an A yet. When we see a B from this state, hasn't ended with an A. If we transition back here, see some Bs, and then eventually see an A, we'll be back in an accepting state. So an example that would illustrate that is if we had something like the string A, B, 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 A. And this A is going to kind of be optional at the end, so we can see exactly how this works. So from Q0, we see the first A, the second A. Just because we visited a final state doesn't mean that we're going to accept. We have to end in a final state. So we see another A and we stay in Q2. If the string ended here, we would accept, but it doesn't. We read the first B, we go back to Q1. If the string ended here, we wouldn't accept because it hasn't ended with an A. We stay in Q1 as long as we see Bs. And if we see this A at the end, we transition back to Q2. And that way we know that only if we end on an A do we accept. And we only got down this path because it started with an A. So the important transitions here are the A that starts, the A that ends, or ends. These are kind of the two ways that the string can end with an A. It either saw a B before that, or the first A before that to be in Q1, or it's seen multiple A's at the end. Can anyone think of a counterexample to this, where this structure does not accept some string that is in this language? The answer is no, because it's the right answer. This DFA represents this language and vice versa. But it's always worth critically thinking when you think you have an answer. Just go back to it and say, is there a counterexample? Does this handle every case? Because there will be times that will fool you throughout the quarter. Any questions, any confusions, anything that I can clarify? All right, I have one more example. Right. As usual, I have some kind of diagram on the slide to show you what an answer would be. Let's go to example 4. The language is going to stay exactly the same from problem 3. But remember that we can add a superscript to that language. What did that say again? What did that terminology mean?
Repeat it a number of times.
Yeah. So basically, we want some way to define what L squared is. Let's take a shot at going back. And here was the mathematical representation of L. What could you have as the mathematical representation of L squared? How could you define that in terms of some mathematical statement?
You just have the same thing. At the end, do AWA.
Close.
Would be AAWAA.
Also close. The reason why Patrick's was close, but not perfect, is that if you define this as W and the repeat as W, then you're making one additional specification that what is between the first and second A here, and between this other A and A have to be the same string, which they don't have to be.
On a new set on the side.
Yep. So let's say we're gonna define this L squared. We can call it something else if we'd like, but we're gonna say L squared is a W sub one A W sub two A, such that now we just say W1 and W2 are members of the set of A, B, star. Extremely close. But this states that now W1 and W2 can be different. Questions on that representation, how that represents the fact that we can have basically any string that this accepts concatenated with any string that this accepts. And the definition of that is this. All right, let's actually go and find a DFA for it. In fact, I'm actually going to go back to this just so you can see the solution to the last problem. And now, what does a DFA for this look like? Using this as kind of the place that we might start. Anyone want to volunteer and come draw the diagram that they have on the board? Sure. The question that I have for you is it an extension of this one?
Similar, very similar.
So-
At the start.
What I will do is I will kind of move it to here so that you have full access to the board. I was gonna ask if you wanted
Oh,
this
right,
here,
right.
and that way you could draw with half of it there.
I would need to cross out maybe one or two connections. Most of it would be almost the same.
Okay,
I give this.
sure. That way, if you're still working, you can continue to work while Nathan draws his solution. Really, really, really close. Really close. So I love all of this extension. I think that's really good. Is there any counterexample that people can think of? State.
No.
It is not a final state. Yeah, I think that was that change here. So it's not a final state anymore.
I have the intention.
Yeah.
A,
B, A, B, A. So what is, if we wanted to break this down into AW sub 1A, AW sub 2A, what would that be? Where are the A's, the W1? I guess it'll be obvious if we just label what W1 and W2 are. Right. So there's no possible location for W1 and W sub 2. Because there have to be A's between the W sub 1 and the W sub 2. So this is not in the language, so we would hope that we don't reach Q5 as we do this. So we have A, B, A, B, A. So we don't reach it. So I think we're okay on this string. Not in the language, don't reach a final state. Any other counterexamples we can think of? One thing that you will learn about me is I love throwing people off. When I said really, really, really close, I meant infinitesimally close. So infinitesimally close that it's correct.
You do like 5 A's and then a B and then an A.
5 A's, 1, 2, 3, 4, 5, and then a B and an A. So we could split this up into A, W sub 1, A, W sub 2, A. So here is your W sub 1, here is your W sub 2. So I would say that just looking at the definition, this is in the language. So this says that we should reach Q5 by the end of this. It's a good example. We do end up there, but I like going over this because it's a reasonable suggestion. So we would have A, B, A, and we end up in Q5 and would accept the string. So that's good. Yep, I like it. I think this is a good suggestion. But a good solution, as we come up with more complicated things that lead to more complicated structures, it will be very easy to make small changes where there are just a few counterexamples that break your logic and your diagram. So it's always worth taking the time that we just did to go back and assume that it's wrong and try to find how is it wrong before we really conclude. I think I've thought of everything here. Questions on Nathan's solution, why this works, why this is a representation of that language? Okay. I'm gonna try to guess, I guess, blow people's brains with the last minute of class. It's unfortunate because that's the solution. And I think that's what was drawn. We are exactly out of time. Non-determinism isn't quite a 1 minute discussion. So we're gonna come back to this tomorrow because it's going to, I think I can give you the teaser for why you should be here tomorrow. And that is that every machine that we use, every program that you have ever written is deterministic. But you could make an argument that what if we could branch, like do an if statement, but do both branches simultaneously? What power would we have if we could do this? This will come into play as quantum computing becomes a thing. The idea behind quantum computing is, can we actually answer the question of, is non-determinism and determinism, are they really the same thing? Because we can't prove one way or the other. So we study non-determinism as a theoretical concept of something that we can't write a program for, but we also can't prove that we can't write a program for it. And it would be really interesting and break the entire world if we could. So we're going to study it, find a diagram that we can use to represent it, and show how we can actually make some theoretical arguments about the world in this world. So I will explain that in a lot more detail tomorrow.